Alright, here we are, continuing with current, resistance, and electric power. So, 17.3, electric current. What is electric current? Well, electric current is the flow of charge through a given area. So, now we're going to start talking more along the lines of wires and circuits and things like that. Charge is our electrons moving through the wire. Now, this is similar to the current of a river, where it's the number of gallons through a place in the river. We can also compare this to students through a hallway. In your mind, you can think of areas of hallways that are easier to get through and harder to get through, and we'll talk about that when we talk about resistance. So an assignment at a break time, and that's to go out to a place in the hallway and count the flow of students past one point in a 30-second time frame. How we calculate the current of these students? Well, we take perhaps the number of students per time, and maybe we count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there. I think it was 10. 10 charges went past that given point, so we would have had 10 in our 30 seconds, a current of 10 divided by 30. That's 1/3 of a student per second. Okay. So let's relate that to electricity. I is current. I equals charge per time. So current is measured in amps, amperes, also known as amps. So 1 amp is equal to 1 coulomb per second. It's named after André Marie Ampère. He's French. Then we have the discussion of alternating current versus direct current. Direct current is what we're going to focus on mostly. That's your batteries powered. Direct current is flow of charge in one direction. Alternating current is what our homes are powered off of. It switches back and forth. There was this great philosophical debate back in the day of Thomas Edison of whether we should use direct current or alternating current for our municipal power supply. Advantages. Direct current is very easy to generate. Alternating current, we not as much. But the advantage of alternating current is you can transport it over long distances, over very, very high voltages with very little loss of electricity. How it would look different. If we were to have a direct current system, our electricity will work just fine. But we'd have to have many, many, many power stations all over the place because you can't transport the electricity at household levels. So we'd have to be generating it at roughly 110 volts, and that's it. Whereas today, we generate our electricity at huge amounts of volts and transport it over the big high power lines. You'll think of Avon Lake and the power plants. It's just to be a very different look to the system. Our alternating current here in America runs off of 60 hertz. I think 60 hertz. I could be wrong. But 60 hertz, and it's not to say we're right or wrong, but other nations don't use 60 hertz. That's why when you travel, you have to get those power adapters so you don't fry your electronic equipment. Simulations. We will be doing these simulations in class, so more on that later. Talking about resistance now. Resistance is, and that's not the right heading, sorry, we're still in 17.3 here, that's just the old book's title. Resistance is a measure of how easy it is for us to change the flow through an object, a wire, for most of our uses. And for this, we will use Ohm's law. Notice that I'm going to show you 3 forms of Ohm's law, and they are all the same. So resistance, R, is equal to voltage over current. Or you could solve for current, where current equals voltage over resistance, or voltage equals current times resistance. These are all the exact same equation, but this is one of those times when I encourage you to actually write it all 3 ways on your equation sheet. Resistance is measured in ohms. That little horseshoe thing is the Greek omega. So ohm, 1 ohm is equal to 1 volt per amp. And it's named after George Simon Ohm, a German physicist who figured out, of course, Ohm's law. It's his law. So let's compare a hallway to a wire. When you change classes, you usually like low resistance hallways to get through. So think of low resistance hallways in our school. What makes them low resistance? Usually they're shorter portions of the hallway, so they're easy to get through because it's short. Usually they're wider. Think of the commons. Usually there's not a backup to get through the commons. No obstructions. If there's trash cans in the way or freshmen with gigantic backpacks, that tends to be in your way as you go. And calmer kids are easier to navigate around. Imagine freshmen when they're all hopped up after gym class. Not easy to get through. What makes high resistance hallways? And you can't, there's nothing there for high resistance. Let's turn the page. These same characteristics hold true for wires and resistance. So low resistance, a short piece of wire versus a long piece of the same wire. Low resistance, a wide, large area wire versus a narrow wire for high resistance. Low resistance, a very conductive material, a less conductive material for high resistance. At low temperatures, we have better conductivity than high temperatures. So short, obviously, it's easier to get through something that's short than something that's long. Wider area is easier to get through because there's more space. A more conductive material, and here we're talking things like copper and gold versus aluminum and steel. Lower temperature versus high temperature. When things get hot, the molecules of the conductor themselves bounce around and interfere with the flow of the electrons. So we want low temperature for high conductivity. This page is not accurate, but you talk about superconductors, and superconductors are very interesting in that at very, very low temperatures, 603 is where the stuff's located on this. At very, very low temperatures, you actually get zero conductivity, which is really cool. But of course, with our new technology, we're getting higher and higher temperatures you can get that. For example, a lot of our classic superconductors are very close to absolute zero, 4.15 degrees Kelvin, 1.19 degrees Kelvin. Well, today we're getting up into, recently we've got 150 Kelvin, which is a negative 123 Celsius, which is something we can actually get to with liquid nitrogen and the like. Okay, we're ready for some homework here. So you have two homework assignments that go with both current and resistance. Your first homework assignment that goes with current is on, follow with me here, page 595, and you're going to do 1 through 5. Yellow makes sense here. 95. That is homework that is on current. Then you have an assignment that is on resistance, and that is going to be found on page 601. Page 601. And this is also going to be, yeah, I know you're probably making fun of me. 1 through 6 here, 1 through 6 on 601. So you got a couple assignments to work on with this assignment, but all of them are within reach.